is the second video for logistic growth and partial fractions for BC calculus. This is a BC only topic, section 6.5 in your textbook. So in the last video, we were looking at integrating rational expressions that could be written with the denominator a higher degree of the numerator that could then be written as a sum of linear-based rational functions. Here, though, if you look at example 3, notice that the degree of the numerator is higher than the degree of the denominator. So this one's a little bit different. We actually can still turn it into partial fractions, though, and integrate just like we did in the last problem. However, because of the fact that the numerator is larger, this really becomes back to the concept of a fraction is a division problem. So we would actually first simplify this by figuring out what it would be if I actually divided that denominator into that numerator, since the denominator is smaller. For example, if I had the fraction 24 over 6, 24 over 6 would simplify to a 4 because 24 divided by 6. So here, 3x to the fourth plus 1 over x squared minus 1 is the same as saying 3x to the fourth plus 1 divided by x squared minus 1. So that means we have to figure out how to divide x squared minus 1 into 3x to the fourth plus 1. Synthetic division is something that you could use, but you can only do that if what you're dividing by is a linear factor. X squared is not linear. So the way that we divide things that are not linear is with long division. So I'm going to add in a page here, and all I'm going to do on this page is the long division of x squared minus 1 into 3x to the fourth. Now, it's 3x to the fourth plus 1, but I don't know if through this process I might have some x cubes or some x squareds or some x's to deal with. So I'm going to put some placeholders there for me just in case I need them. I may not need them. All right, so this is a review from a while ago. If we're going to do long division, you take the highest degree term of what you're dividing by, and you go term by term of what is under the divisor there. So 3x to the fourth. Well, if I was going to turn x squared into 3x to the fourth, it would need to get multiplied by 3x squared in order to make that happen. So then you take that number that you wrote above your divisor, so that red 3x squared, and you multiply it by everything that you're dividing by. So 3x squared times x squared is 3x to the fourth. 3x squared times negative 1 is negative 3x squared. Now, if you remember long division from with numbers, the stuff that you wrote down here is then subtracted all the way through. So I actually find it helpful to maybe go through and change all of my signs so that I don't forget that I'm subtracting those things. So 3x to the fourth minus 3x to the fourth is 0. That's what we wanted to have happen. I can skip over the x cubes because I don't have any. And then I have 0x squared plus 3x squared. So that's 3x squared. I'm going to bring down the 0x and the plus 1. And I'm going to keep repeating this process until I can't divide by x squared minus 1 anymore, because what I have left is a smaller degree than the x squared degree. So again, we go back to the x squared. And I want to turn it into a 3x squared now because that's what I have at the bottom of my problem. So x squared would need to get multiplied by a positive 3 in order to give me 3x squared. And then that positive 3 would also get multiplied by the negative 1 so that I have a negative 3. But remember, you're subtracting everything. So I change my signs there. The x squareds are going to cancel. I don't have any x's, and 1 plus 3 is 4. Now, it is impossible to multiply x squared by something and have it turn into a 4. So the 4 is the remainder. But we are not in elementary school anymore where you can say that your answer is 3x squared plus 3 are 4 for the remainder of 4. Your answer would be 3x squared plus 3 plus the remainder divided by what you had in the denominator originally. All right, so this now, if I go back to my problem, I can now write this integral as the integral of 3x squared plus 3 plus 4 over x squared minus 1. because that's the same as saying 3x to the fourth plus 1 divided by x squared minus 1. So integrating the 3x squared is going to be easy. I can use reverse power rule. Integrating the 3 is going to be easy. And then I come to the 4 over x squared minus 1. So 4 over x squared minus 1, that's now a rational function. So that's the part that I've got to do the a over something plus b over something. So get a different color here. 4 over x squared minus 1, if I factor that denominator, it is x minus 1 and x plus 1. But I don't know what my numerators would be, so that when I do get common denominators and add them together, I end up with a 4. So then remember, the first thing we want to do is we want to eliminate the denominators. So we're going to multiply through by x minus 1, x plus 1. So the first fraction, the denominator cancels out, and we have a 4. The second fraction, the x minus 1s cancel, but we're still multiplying by x plus 1. And then the third fraction, the x plus 1s cancel, and we're multiplying by x minus 1. So that gives us 4 equals ax plus a plus bx minus b. And again, if you remember from the last problem, we then group the like terms. So on the left-hand side, I don't have any x's. So ax plus bx should add up to being 0 x's, which means a plus b equals 0, or a is equal to negative b. Then as far as constants go, I have 4 equals 1a minus b. So this is the point where in the last example, they were more complicated, the two equations that we had left with the a's and the b's in them, so we used some elimination. Honestly, since I know that a is equal to negative b over here, I'm just going to go rewrite a as negative b. So then I have 4 equals negative 2b. Negative 2 is what b would be equal to. So a is negative 2, which is positive 2. So going back to my integral up here, I have the integral. We'll group the 3x squared plus 3 together because those are easy. And then I have the integral of positive 2 over x minus 1 and the integral of negative 2 over x plus 1. And I'm running out of room for my dx. So now the hard part's over. We just got to integrate those things. 3x squared is going to integrate back to x cubed. 3 is going to integrate back to 3x. The x minus 1 being in the denominator, if we do u substitution, that becomes 2 natural log of the absolute value of x minus 1. And then the next one becomes negative 2 times the natural log of the absolute value of x plus 1. And then the plus c at the end, which is perfectly acceptable as a free response question answer. You have now integrated everything, so that could be your solution. But as we discussed in the previous video, most of the time in the multiple choice, they're going to combine the logs together. And if you notice, these logs actually do have the same coefficient. So we could leave the 2 in front if we wanted to. And it would be, since the second log is being subtracted, it would go to the denominator like that. Or potentially you could then take the 2 and make it the exponent, but it would be the exponent of the whole fraction. And we wouldn't need the absolute value anymore because we're squaring it. So the squaring is going to make things positive anyway. So the absolute value would be redundant. So this would more than likely be your final multiple choice answer on a problem like this, 20 minutes later when you finish doing it. All right, so there's example 3. So now I want to look at example 4, hopefully in this video too. I hope we'll have time for that. So we have a differential equation that we are trying to integrate. So I'm essentially just trying to integrate this. I'm going to move the dx over here. So if you notice that the denominator is already kind of factored for us, although not quite. And if we were to distribute it out, its degree would be a third, x to the third, and the numerator is x squared. So this is more like example 2 that we've already gone over, where the numerator is a smaller degree than the denominator. So what you would want to do, though, is if you split that up, you've got 6x squared minus 8x minus 4. And if we fully factor it, we have x plus 2 times x minus 2, then times x minus 1. So since we have 3 factors, that actually means that we would have 3 linear-based rational functions that we would put together to get it. So that's a fun one, right? But other than the fact that there's 3 of them, my process is not any different. I would want to multiply everything by the least common denominator. So we would have 6x squared minus 8x minus 4. Then the a is going to get multiplied by x minus 2 and x minus 1. B is going to get multiplied by x plus 2 and x minus 1. And then C is going to get multiplied by x plus 2, x minus 2. So you got a whole lot of algebra going on here. So we've got 6x squared. You know what? I think I'm going to go ahead and group my individual terms. And a negative 8x and a negative 4. So when I'm distributing here, I think I'm going to FOIL before I distribute the variable through, or the a, b, or c through. So this would be x squared minus 3x plus 2. So when I distribute the a, I've got ax squared minus 3ax plus 2a. So now they're kind of already grouped by like terms. The b would be x squared plus x minus 2. So that would be bx squared plus bx minus 2b. And then this would be x squared minus 4. So plus cx squared. I don't have any x's for him. And then minus 4c. So if we... All right, so when we remove the variables, then we get 6 equals a plus b plus c. This one is negative 8 equals negative 3a plus b. And this one is negative 4 equals 2a minus 2b minus 4c. So that one's not any different. With the center one there, since it only has 2 variables in it, that's really easy to solve and get that b is equal to 3a minus 8. Then I could go to either the first or the third. If I go to the first equation, I then have a plus 3a minus 8 plus c. Add the 8 over here, we get 14 equals 4a plus c, or c equals 14 minus 4a. So then if I go to the third equation, I can now write everything in terms of a. In place of the b, I can put 3a minus 8. And in place of the c, I can put 14 minus 4a. So that gives me negative 4 equals 2a minus 6a plus 16 minus 56 plus 16a. If you bring all the constants over to the left, you get 36, and all the a's combine to be 12a. So a is 3, which means that b is 1, and c is 2. So your integral is now the integral of 3 over x plus 2 plus the integral of 1 over x minus 2 plus the integral of 2 over x minus 1. So I want you to pause the video now and see if you can integrate from there to get the final answer. All right, so I moved to a whole new screen to finish my problem out from there, rewrote it, integrated the 3, and ended up with one gigantic logarithm as my final answer. So check and see if you and I agree with each other.